Okay guys, let's go ahead and do our lecture for section 4.5. This will be the first out of 2 videos. Section 4.5 is called Linear Approximation and Differentials. So basically what's happening here is we know that if we have a differentiable function, I'll write some of this down. So if we have a differentiable function f of x, remember differentiable just means that we can take the derivative. We know that f prime of some point alpha is the slope of the tangent line of f of x at that point x equals alpha. And we also know that this is the instantaneous slope of our function f of x at alpha. Right, so this is what we've been talking about all semester. A derivative is just the slope of a tangent line, instantaneous slope of our function. And a lot of times we've been using information about our function to estimate things about the derivative, and now we're going to do the opposite. So basically, if I have a graph, I think I draw the same graph every time, but anyway, let's just say our graph looks like that. And let's label a point alpha, and then I'm going to draw in my tangent line. Ooh, that was a pretty good tangent line. Okay. So if we look here, if I were to like zoom in really close on this point, I guess I kind of drew it badly. This should not. Anyway. If we zoom in really close to this point, we can see that our tangent line here has kind of a little region around here where it is very similar to the values of our actual function f of x. So what we're actually going to be doing is using the tangent line to estimate values on our function. So that's our goal. And this is called a linear approximation because a tangent line is a line. Okay? So, basically, what we would need to do is find like a general equation for any given tangent line if f of x is differentiable. So for the rest of this section, just assume f of x is differentiable in all of my general statements. Okay, so basically our goal is to find the equation of the tangent line given some function f, and we'll be using that to estimate different points, because if we find our tangent line, we could use say, this point on our tangent line to estimate this point on our actual f of x function. Okay, so let's see here. Our general tangent line looks like this. We have point slope form, so we have y minus our y value, which is just f of alpha. I guess I should say this is the tangent line at alpha. And that is equal to f prime of alpha, our slope, times x minus alpha, where alpha is our value of x in our point. Okay, so we can rearrange this, because remember, our goal is to estimate something about our function, which means our goal is to estimate this value, y, using this value on our tangent line. Okay? So we have y is equal to f of alpha plus f prime of alpha times x minus alpha. So that's our general tangent line. All right, and so then for the next part, this is your kind of cheat sheet moment. We're going to be calling this linear approximation L. So the linear approximation L of x using the tangent line of f of x at this point x equals alpha is, we have our function f of x, and it's approximated by our function L of x, which is equal to exactly what we just did over here. So we know for our tangent line that y is equal to this, and we also know that f of x is very similar to our tangent line at the points around where our tangent line was made, right? So if I have my tangent line of a certain point, in this case alpha, if I have points around it, those values on my actual line, my actual curve, are very similar to my tangent line. So that's what's happening here. I have my actual curve, and I'm approximating it using my tangent function. So I have f of x is approximated by L of x, which we're just calling our linear approximation. That's just like the symbol we're going to be using for it. And L of x is equal to exactly what we had y equal to up here. So f of alpha plus f prime of alpha times x minus alpha. Okay? And this is for x values near alpha, right? So if I look back at my first example, I couldn't really use this line to estimate a value over here because the difference is really big. So I want to make sure that I'm doing my estimates for values near alpha. So depending on where I want to estimate, depending on what x value I want to estimate my function at, I need to pick different values of alpha for that to work. And we'll do an example. Okay, so that was your cheat sheet information. Now we're going to have an example. So this is a two-part example. First of all, find the linear approximation to f of x equals the square root of x at x equals 1, and use it to approximate the square root of 1.1. Okay, so just to kind of point out what we're talking about in terms of notation here, we're finding the linear approximation, so that's going to be using our formula up here. So linear approximation is just L of x and then at x1 means we're going to be setting alpha to 1 and then using it to approximate the square root of 1.1, so this portion means that we're going to find our L of x and then we're going to find L of 1.1. So we're going to plug in 1.1 for x to approximate it. Okay, so that's just a breakdown of what we're using as our terminology. And then for part B, we're going to use the same linear approximation to estimate the square root of 0.1. Okay? So, for part A, our first step is to find L of x for alpha in general. So we're not going to pick an alpha value yet. We're just going to leave alpha as a variable in there. So we know that L of x in general is equal to f of alpha plus f prime of alpha times x minus alpha. Okay? And in this case, our f of x is equal to the square root of x, which can be rewritten as x to the 1/2. So we get L of x is equal to alpha to the 1/2, because f is x to the 1/2, and we're plugging in alpha for f, or x. Okay, and now we need to take the derivative of x, or sorry, the derivative of f with respect to x and plug in alpha. So just as like a little side note over here, the derivative with respect to x of f is 1/2 x to the negative 1/2. So that means over here we have 1/2, well, really 1/2 to the square root of x. This is the way you would write that. Times x minus alpha. Okay, so that's our general formula. Step 2 is going to be plug in alpha equals 1. So then I like to denote stuff as L sub alpha of x to keep track of the alphas. But it's just my own personal notation. It's not really everyone, I just think it helps to remember what your alpha is. So I would say L sub 1, because alpha is equal to 1, of x is equal to 1 to the 1/2 plus 1/2 times the square root of x. Oh, sorry guys. This shouldn't be x. This should be alpha. Okay, yeah, because I took my derivative and then I needed to plug in alpha. Anyway, so now down here I need to plug in 1 for the square root of alpha times x minus 1. Okay, and if I rewrite this, I get 1, because 1 to the 1/2 is just 1, plus 1 over 2 times the square root of 1 is just 1/2 times x minus 1. Okay, so that's my estimate. And now, step 3, plug in 1.1 for x. And that'll give us our approximation. So we have L sub 1 of 1.1 is equal to 1 plus 1/2 times 1.1 minus 1, which is 1 plus 1/2 times 0.1, which is just 1.05. Okay, so what this is saying, and what we would write as our answer, is f of 1.1, which is equal to the square root of 1.1, is approximately L sub 1 of 1.1, which is equal to 1.05. Okay? And we can compare it to a calculator value. Which says that the square root of 1.1 is equal to 1.0488, etc. So our error is approximately 0.0012, which is good. Just in general, there's no like exact way to know something's good, but because we're just dealing with random numbers, I would say being 1/1000th off is pretty good. Anyway. Okay. So then, also, I'm sure you guys are like, why would I ever use this method to approximate something when I could just use a calculator? And the answer is, I don't really know. I don't think this is important. But you do use this similar approximation method in Calculus 2, so for those of you going on, this is really important. And this is just a way to practice these skills. So this actual skill you will not be needing, but this process is important. Anyway, okay, so for part B, we already have our general function, right? So our step 1 from above is done. We had L of x is equal to alpha to the 1/2 plus 1 over 2 times the square root of alpha times x minus alpha. Okay, we already did that. Now step 2, we're going to be plugging in alpha equals 1, which we also did above, and we get L sub 1 of x is equal to 1 plus 1/2 of, or times x minus 1. Again, we already did that. And so the only difference is step 3, where we plug in 0.1 this time for x. So if we look up here, this little bit here, the estimating 0.1, means that we want to find L of 0.1. So we're going to have L sub 1 of 0.1 is equal to 1 plus 1/2 times 0.1 minus 1, which is 1 plus 1/2 times negative 0.9. So this gives us 0.55. Okay, so using this, our answer would be that f of 0.1, which is equal to the square root of 0.1, is approximately equal to L sub 1 of 0.1, which is 0.55. But if we check our error, we'll see that this isn't a really good estimate. So we could do a calculator and see that the square root of 0.1 is actually equal to 0.3162, etc. So we're pretty far off there if you guys look. Up here, we were only off by like a 1,000th. Here we're off by a 10th, or 2/10 actually, which is pretty bad in comparison. So we know that this isn't a great estimate. And a question we can ask ourselves is, what would be a better way to estimate it? A possible answer is we could let alpha equal 0, but if we think about this, f prime of 0, which we would need to calculate, because remember we need f prime of alpha, f prime of 0 is equal to 1 over 2 times the square root of 0. Hold on, guys, I'm double checking my... Yeah, sorry. Which isn't defined. Right, because we can't divide by 0. So this doesn't work. So we could try something that's not 0, but is still close to 0.1. And I'm going to suggest something and then explain why I'm going to use it. So 0.1 is pretty close to 0.09, right? We're just 1/100th off. And if you look, that's the same as 9 over 100, which is nice because we're dealing with square roots. And the square root of 9 over 100 is 3 over 10, so it's pretty easy to work with. We don't get some crazy irrational fraction. Okay, so let's try doing this and see if we get a better result. We would have L of 0.1 here, let me, not L of 0.1, just L sub 0.09 of x is equal to, I need to go back to my general x function. Okay, up here we have L of x is equal to alpha to the 1/2, so this would be the square root of 9 over 100. I'm actually going to rewrite this. I guess I'll leave it as 0.09, but note that this is 9 over 100. Okay, so that's the square root of 9 over 100 plus 1 over 2 times the square root of 9 over 100 times x minus 9 over 100. Okay, so we could simplify this. We'll get L sub 0.09 of x is equal to 3 over 10 plus this becomes 3 over 10 in the denominator, and then when we multiply it by 2, it becomes 6 over 10, and then we flip it because it's dividing by a fraction, so it's actually the reciprocal. Okay, so we have 6 over 10, and then it is going to be multiplied by x minus 9 over 100. Okay, if I made any errors, I'm sorry. I know the final answer is correct. I'm just doing arithmetic on the fly, and that's not my specialty. Anyway, alright, so this is our estimating function. Then we're going to plug in what we're estimating, which is 0.1, and we get 3 over 10. Also note 0.1 is the same as 1 over 10, because we're going to use fractions since they're easier to work with. We get 3 over 10 plus 6 over 10 times 1 over 10 minus 9 over 100. And let's just make this 10 over 100. For math ease, I guess. So we have 3 over 10 plus 6 over 10 times 1 over 100, which, if we add this all together, becomes wait, why is it? Uh-oh, guys, I think I made an egregious error. What have I done here? 10, 3 times 2 is 6. No. Okay, I'm still pretty confident in my answer. I'm just not sure how they simplified everything. Anyway, supposedly this is approximately 0.3167, which obviously is much closer to 0.3162, etc., which was the calculator's answer. So we're much happier with this estimation. Okay. So that's basically the only example I want to do for this right now. In the second video, I'll talk a little bit more about just some things to observe about our estimations here, but this is basically the type of problem you would be doing. Alright guys, see you in the next video.